Hello, my name is Dorin Pitigoi, and I would like to have a short presentation about the challenges of measuring substrates that are not paper-like, substrates that are largely used in large format printing, and that requires a specific approach when you measure them, you view them, when you characterize them, you profile them, and so on. We are going to apply two very important concepts. One is printing the expected, while we measure the same way we see. So what are our challenges? Typically, we print on paper, which is a very flat, non-texture substrate. But in large format printing, we have a variety of substrates that doesn't look like paper. We have perforated substrates, we have low opacity substrates, we have Bagley type of substrates, we have texture substrates. All of them require a specific approach when you establish a metrological protocol. So in graphic technology, we have a very important ISO standard. Most oral devices that we are using in graphic technology, the 450 devices, are complying to this standard. It's called ISO 13655. We have the measurement conditions there. We have some backings that we are using when we measure different type of samples. And typically, this measurement condition and the backing need to be consistent with the characterization data set that we are going to use for simulation during printing. But not always the backing, for example, need to be exactly the same type of backing that we use to create the characterization data set, the reference one. One of the most important things of ISO 13655 is that it requires that there is a meaningful interpretation of the measurement data. In a very simple words, it means that the colorimetrical data that you are getting out of the measurement need to be consistent with the visual appreciation of the human observer. And this it's applicable for what is called the 450, 045 geometry and the D0 transmissive geometry. These are the two types of geometries that are widely used in graphic technology. So in order to close the loop, we also need specific viewing booths or transparency viewers. So the observer has the right viewing condition when it's observing the same reproduction that we measured. Non-paper-like substrates, technically, we can treat them like a paper one. A non-paper-like substrate means it has specific properties that requires a specific approach when establishing the metrological protocol. In the Fogra specification for large format printing that I gave the presentation yesterday, I said that typically we can apply in the same way the metrological protocol that we do for paper-like substrates, for non-paper-like substrates, when they are able to pass the so-called visual plausible testing. And this is a very simple test that we can do to our non-paper-like substrates in order to determine if our measurement protocol, including the geometry, the measurement aperture, the backing, the software used, the mathematical algorithms made for computation are consistent with the visual perception of the human observer. We also need to take into account that the data sometimes need more than one measurement. It needs averaging, it needs smoothing, and we need to use specific instrument characteristics in order to get the meaningful readings from our sample. Very good example is what a scanning measurement device will do. It's basically continuously illuminating a target, and it's taking over 200 measurements per second, and it's having a built-in hardware algorithm to average all these 200 measurements. That's why we need wider patch sizes. And a good example is a Fogra media wedge for LFP, which has a 19 millimeter patch width. This control strip is made in such a way that you can read basically with any devices available in the market for the graphic technology. It's using this concept of the continuous illuminating scanning devices that are taking many, many hundreds of measurements per second. Wider patches means that we have a lot of averaging. So the quality of our measurement, it's improving a lot. we don't have separators. Typically, if you think about the i1 Pro or i1 Pro 2, you have separators between the patches. But all of these devices, they have a built-in mechanism to discriminate when they jump from one patch to the other. It's enough that you have a jump of over 5 delta E that the device figures out that you are moved to the next patch and is starting a new averaging session. Basically, the concept is that for large format printing in general, it's recommended to use larger patches for scanning. A good example is this chart, which was built with the support of Digital Printing Working Group. This is a technical committee that is hosted by Fogra. And the concept was to apply the same knowledge that we use to create the media Fogra wedge, the Fogra media wedge for large format printing, to create a universal large format printing chart. This is based on the ISO 12642 Part 2 standard, which you will know as the name of IT 87.4. We added several patches for uniformity, and we created basically a 12-pages chart that can be read by any measurement devices available on the market. And you can download this chart from the Fogra website. And you can use it for profiling or for any other type of evaluation. Now, I mentioned this visual plausibility test. It's a very simple test. It's basically saying that in order to figure out if your output printing condition, I mean the substrate, the ink, the printing mode, the printing system, all these variables that are making your printing combination, if you measure the result, the printed matter, you need to get consistent data with visual appreciation. And the visual plausibility test, it's made in such a way that it's giving you relevant information if you succeeded in doing the right measurement. It's a very simple process. What you need to do is basically, instead of proofing traditionally, you have the Fogra 39 characterization dataset or ISO-coated V2, and you make a contract proof according to ISO 12647 Part 7. Well, here we do the same, but instead of using this traditional reference printing condition like Fogra 39, we take our output printing condition and use it as a reference. And then we proof it, and we put it side by side with our actual substrate that we use for measurement, and we compare them visually. If the reproduction is consistent between the so-called proof of our output printing condition and the actual printing condition that is made on the real substrate, then our test is successful and our measurement protocol is consistent with what the substrate characteristic imposed on the measurement protocol. So, very simple thing. It's fully described in the both Fogra PSD manual, Process Under Digital, and also in the Fogra specification for large format printing. Now, one type of substrates that require specific approach are the perforated substrates. They have a very simple characteristic. They have a ratio between the holes and the continuous part of the substrate, and this perforation have a size. If it's a one-way view graphics, for example, you have holes. If it's mesh banner, then you have a mesh of material that is creating this substrate. So how do you measure this? The substrate can come with a liner, because this is related to the addressability of the printing technology. Some printing technology require that your perforated substrate have a liner. Some other technologies are having simply an ink collector, so the ink that is passing through the holes is ending up in this ink collector. But the question here is, how do we measure this? What we find out in practice is that printers, generally, they do not measure it. They simply use a surrogate media setup coming from either a self-adhesive vinyl, for example, for one-way graphics, or from PVC banner for the mesh. So they do not measure it. They simply take a surrogate media set and they use it for printing. And the results are, most of the time, acceptable, but not of a very good quality. So how can we improve this? A very simple thing. Every time you want to measure this kind of substrates that have a specific behavior, you simply need to understand what is the relation between this substrate and the light that it's either reflected or passing through or absorbed by the substrate. So you simply need to substitute yourself to the measurement device. When you do that and realize what is happening, it's much easier to build up a metrological protocol. For example, this is a perforated substrate. What it means? It means that the light that is passing through the holes will never return to the user, to the observer. We can replicate the same thing for the measurement device, but simply putting a black backing under the perforated substrate. A very simple procedure shows that technically, when we do the measurement of a perforated substrate with the liner on, so the ink is not meant to adhere on the liner, it's meant to adhere on the substrate. We do the measurement and we see that they are very non-uniform, which means that the ink that was deposited on the liner is creating a lot of inconsistency in the measurement. So this is not practical to use. I mean, it's completely useless. Then we take it off the liner and we put it on a white backing. You know, the ISO 13655 defines two types of backing, the white backing and the black backing. We put it on white backing and we see that our measurement quality improved, but the visual consistency is bad. I mean, the light passing through the hole is reflecting from the white backing and it's ending up to the observer. It's not, again, not a good approach. Then the last choice is to take it off the liner and put it on a black backing. And this time, we successfully replicated what is happening with the light passing through the holes of the substrate. The black backing is simply absorbing and not returning the light into the measurement head of our device. And the result of the measurement shows very easy that the measurement is consistent, and our visual appreciation of the targets also show that it's consistent with the perception of the observer. So the next question is, well, how big need to be the aperture of our measurement device in order to get good quality measurement out of such a substrate? So we have an annex in our measurement standard, the ISO 13655, that refers actually to the relation between the screening, you know, either in conventional or in digital printing, what is the screen size or screen width relation to the aperture. If we apply the same approach to the perforated substrates, when we have a ratio between the holes and the solid part of the substrate and the perforation size it's defined, we can easily determine that for a 1.6 millimeter perforation, we need at least 19 millimeter aperture. But this is not possible because the highest available aperture size in the market, it's coming from Barbieri, it's a spectral FP, it has an 8 millimeter aperture. Of course, there are some other industrial equipments, but they are not using the 45-0 geometry. They are using the sphere optic geometry, and these type of devices are not common in graphic technology, nor do they correlate very well with this type of geometry. So we have to do a measurement using an 8 millimeter aperture device, and this device has a feature. Its software, it's allowing us to do up to 5 measurements by moving the measurement head with a step in different direction around the central point of the patch. And this is very useful because basically in this way we create a so-called virtual aperture. And instead of using a 90 millimeter aperture size device, we use an 8 millimeter one with this step average increase. The result can be easily seen if we measure the characterization chart, that universal big chart with 12 pages, and we create a profile. We measure with 6 millimeter, we didn't do any averaging, no smoothing of the data, and we can easily see that the quality of the shape and the size of the color gamut is very inconsistent. The surface is not uniform, it doesn't look nice. Then we do the same chart, and this time we measure with 8 millimeter aperture, and we did a lot of averaging, and we did this 5-step increase around the central point of the patch, and we can see easily that the quality of the color gamut shape improved drastically, which showed that the data that was used to create a color profile, it's more consistent. So by just substituting ourselves to the measurement device, we can easily understand what is the relation between the substrate and the light and the resulting interaction, how it do affect the perception of the result. And by applying this method, we can actually measure these kind of perforated substrates. The question here is how this do reflect in numbers. I mean, we can do the same thing, you know, by simply doing our proofing test. So we print it using the color profile we generated. We use Fogra 39 as a reference printing condition, and we output it on our one-way view graphics self-adhesive vinyl. measured according to the procedure I just mentioned. We use a Fogra media wedge LFP, and then we check the measurement result against the process standard digital media relative tables. And we find a very interesting thing. We took a self-adhesive vinyl. This is a continuous solid substrate. We use its media set to simulate our reference printing condition, and we got a very good quality reproduction. By the norms of Fogra PSD, this is a level A color accuracy reproduction. Then we did what most of the printers will do. They will simply take a self-adhesive vinyl setup and use it for the one-way view graphics. And we can easily see that our measurement of the Fogra media wedge, it's failed. We didn't even manage to achieve the level C. The average and the maximum are not good enough. And then we applied the third measurement over a media set that was created using the methodology I just described. And you can see easily from the numbers that the quality of the reproduction drastically improved. We actually managed to reach a level B quality, which is for a perforated substrate, which is quite nice. So this is what we do. We have here a very good example how this method, it's changing the color appearance when it's reproduced on the perforated substrates. You can see here a car door. The solid part of the door was printed on self-adhesive vinyl, but the window, it's collated with one-way view graphics. And you can easily see the color perception between the perforation area and the solid area. They are quite consistent. Visually, you can see from the picture that the colors are blended smoothly between the solid area and the perforated area. We also asked several printers if they would like to put this methodology in practice. And they responded positively after seeing such an example, and they applied the methods for both mesh banners and for one-way view graphics. And all of them, several months later, provided the feedback that the method is quite successful and it's a huge improvement of the procedure of not measuring anything. Another challenge is coming from most of the textile substrates or the interior decoration substrates. Most of them are either they have a texture, and they also have a different level of opacity. They are not completely opaque, which means that whatever is behind such a substrate, it will be visible from behind. So if your substrate is printing on the back side, or the transparency level, the translucency level, it's low, that means the light will pass through the material and everything that is behind will be visible. Good example are the flags. The flags, they don't have a solid, background. So the light is passing through them and will never return to the observer. One of the things that we find out is that even if the measurements are consistent, you have your characterization data set measured on white backing, you output it on your flag material, it's consistent if you measure it on white backing. The same thing if you do on black backing. But visually, the black backing media set, the one measured from the black backing, was more, the comparison was much better visually than the one resulting from the white backing measurements. The same thing goes for the texture substrates. Here, the importance of the aperture size or virtual aperture used for the measurement is very important. If you use a small aperture for your measurement device, your measurement will be not consistent because the texturization of the substrate will affect the quality of the measurement. Backlit self-adhesive substrates. These basically are typically self-adhesive vinyls, but they are meant to be either transparent or translucent. And you take them off the liner and you put them on glass or on acrylic, and they are illuminating from behind, or they are simply allowing the light to pass through. How do you measure this? Because they are coming on the liner. If you take it off the liner and put your measurement device, will get stuck. So a very simple way to use it is to actually use a foil, a transparent foil that has a thickness of, let's say, 80 microns or 300 microns. Anything will do. We do not prefer very thick foil because that will increase the chances that the light will get scattered inside the foil. And we put our self-adhesive vinyl on top of this foil. In order to use the foil for this approach, the foil needs to be not to affect the measurement too much. It's a very easy way to do it, actually. If you initialize your spectral FP, it will initialize, so you don't have anything between the measurement head and the diffuser. That's your initialization. And if you compare then, using the spot color measurement in their software, if you compare the result of this initialization as a reference and the foil as a sample, the closer they are, the better the foil is. Typically, we don't want to have it affecting color, so this means that the deviation of the CA value and CB value need to be lower than 1, and the lightness difference need to be lower than 2. If the foil is passing this simple, qualification testing, then we simply take our backlit self-adhesive vinyl and put it on this transparent foil, and we can actually measure the substrate. Another problems come from the backlit substrate that are thick. You have glass, you have plexiglass, you have acrylic. They are coming in different thicknesses. The problem with this substrate is that the more the thick they are, more light will either get scattered inside the substrate. The substrate has an internal structure, so the light will travel all over the structure, or you get an outside interference from the light in the environment. So sometimes such substrates are impossible to measure. And you will see that as soon as this substrate thickness is increasing, the quality of the measurement decreases because the amount of energy that is ending up in the measurement hand is diluted inside the substrate structure. Typically, if you have a choice, do not measure very thick substrates. So try to find the thinner version of the same substrate. So if you have like acrylic and it's coming in 1 millimeter, do not measure 5 millimeter thickness. Measure the 1 millimeter one. It's the same substrate, but because of this limitation, it's more preferable to measure a 1 millimeter substrate instead of a 5 millimeter one. Typically, we find out that as soon as the thickness of the substrate it's exceeding 3 millimeter, your measurement quality will deteriorate and you won't get meaningful information from your measurement device. But some substrates, they do not have the choice of measuring, in 1 millimeter thickness. They come only in 5 or 1 centimeters. How do you still, measure those? The good part is that most of these substrates are actually printed using UV curable technology. So most of the ink, it's on the top of the substrate. You remember the transparent foil that we used to measure the self-adhesive vinyl? Well, we can use it as a surrogate substrate. So instead of actually trying to measure, the glass or the acrylic or whatever it's your substrate, use this transparent foil for measurement, create your media set, and use it as a substitute media set for your substrate. If you want to know if it's working, you simply put side by side an output on the foil and an output on the glass or on acrylic, and if they are visually matching, then basically you did your job and you were able to measure and create consistently the media set. Thank you very much. This was my short presentation, just to give you an idea how you can deal with substrates that at first glance are not necessarily, easy or simply to be measured. If you have any questions, feel free to drop them. Thank you very much.